Good afternoon, Dr. Sandeep Kumar Singh. Actually, you are muted.
Sorry. Good afternoon. Yeah.
So, with your permission, can we start the session?
Yes, sure.
Okay. So, welcome to everyone to this another session in on quantum communication. Today's session would be focusing particularly on quantum internet and quantum network. And we have an expert speaker who is Professor Sandeep Singh. So I'm going to read out his short biography. Professor Sandeep Singh is an assistant professor in the Department of Electrical Engineering at the Eindhoven University of Technology, Netherlands. He is currently on leave from Indian Institute of Technology, Roorkee, India. He received his master's degree from IIT Madras and PhD degree with the highest honors summa cum laude from the Technical University of Braunschweig, Germany in 2019. During his PhD, he worked on the design of elastic optical networking systems. From 2019 to 2021, he worked as a research scientist at the German Aerospace Center in the Institute of Communication and Navigation, Germany. He was a postdoctoral researcher at the University of California, Davis, USA from 2021 to 2023. During his postdoctoral work, he worked on the distribution of entangled photons over quantum wrapper network. Additionally, he developed a software-defined networking-enabled data center testbed for intelligent routing and switching. He has received 2 major sponsored research projects within a span of a year since joining IIT Roorkee in the quantum optical networking domain with the National Quantum Mission and the Indo-US Technology Development Fund. His group focuses on developing quantum optical networks, data center networks, and resource allocation methods in optical networks. So we are grateful to him for accepting the invite to be speaker in this FDP, and I hope the participants will enjoy your knowledge. So over to you. You may take the control of the session. Thank you.
Yeah, thank you, Rajendra ji. So thank you, Professor Rajendra Martwal, and thanks all the attendees for joining this lecture. So let me share my slides. So can I share? Yeah.
Yes, you can share. Once you share, this will go off. In the meantime, I request you to take 5 minutes break around 3 p.m. so that we can split your live streaming into 2 different videos.
Okay.
And do you want me to read out the questions on the WebEx, or you would be able to do it on your own? When the participants would be asking through the chat windows. They can't directly interact with you.
Okay. So I will, if there is any questions, so I would like all the attendees to ask questions in between, and it should be like an interactive, not. So if because while I will be presenting and sharing screen, I'm not sure if the questions will be visible to me or any chat pop-up will come. So you can point me out if there is any, and then I can.
Okay, so in that case, I will just interrupt you in between. If there is a question, we can just discuss that.
Yeah, I can take a look and answer. Okay, so yeah, thank you again, Professor Rajendra. And let me maximize it. So do you hear me clearly, or should I use the microphone?
No, it's perfectly fine.
Okay, that's good. So let me begin. Let me maximize the slides. Okay, so I hope all of you can see my slides. So
yes, the slides are visible.
Okay, thank you so much. So yeah, thank you all for Rajendra ji, and thank you all for attending, and thank you Rajendra ji for introducing me and calling me to interact with all the faculty development program attendees today on the topic of quantum internet, opportunities and challenges. And the second topic is quantum network topologies and protocols. So yeah, let me go to the agenda of these 2 talks, basically. So I will be giving you the introduction and overview of quantum internet, networking topologies, opportunities and challenges. In the part 1, I will introduce about the quantum internet and what is the quantum internet, how is it different from the classical internet, how the quantum internet has been adapted from the layered architecture which is already present in the classical internet. What are the current scenarios and challenges? In part 2, I will be focusing on network layer topology, quantum network protocols, my past and current research. Though, I mean, the quantum network, if I as I will introduce shortly, so it's a kind of, quantum internet is nothing but the interconnected quantum networks. So both are actually as an integrated thing. So we will see like the mixed slides. Okay, so before I go to the motivation and why do we need quantum internet, let me just define what is a quantum internet, right? So quantum internet is nothing but network that interconnects the quantum computers or nodes to transfer quantum information, right? The classical internet is also defined in the same way. So as you see, the internet means interconnected networks, as simple as that. And in quantum internet case, it transfers the quantum information, quantum data, right? So main motivation behind this quantum internet is to enable applications that are out of reach for the classical internet. So today's internet have some merits and demerits which we will discussing in the coming slides, but they might not be able to to carry, I mean, some of these applications, or for example, how today's internet is not secure, right? So if we want to have the secure communication, right, we need the quantum internet, right? And why it's not secure, I mean, we can discuss in the coming slides. And also, if we want to have distributed computing, right, then the quantum internet can interconnect, right, various quantum computers on which distributed programs can run, right? And then you will need to send the data from one computer to another to next, and so on, to run the parallel programs, right? So that you can have the you can run even the powerful programs in a distributed manner and in a reasonable amount of time. So if you look at many of these AI applications, ChatGPT, or there are many different models. So they run because they are huge. There are billions of parameters, so they are run in parallel, and finally the models are merged and final model is built. So what we need, one computer cannot solve this problem. What we need is the distributed computing, and quantum as a quantum distributed computing can solve this problem. And in order to network these computers, we need the quantum networking, as you can see here. So, and third application is the sensing and metrology, right? So quantum has an edge over the classical. Shortly we will describe why. And even in that case, we will need a network, right? To run these different applications, what we need is the quantum networks, right? And as I said, quantum internet is nothing but the interconnected networks which transfers the quantum information. Okay, then the question is, why do we need quantum networking or quantum internet, right? So basically, today's internet has several challenges. It typically uses the best effort services provided by transport control protocol. Let me use the pointer and laser pointer. Okay, so as you see here, so TCP/IP we call it internet protocol, and scalability is another problem. Data security is the big problem. That's what quantum can solve some of these problems. So I mean, at many times we hear about the security breach, right? So that if that can be solved, that will be kind of very good actually. Energy per bit few minutes we will see how energy per bit is a problem in the classical and how quantum can solve it. Information rate per photon. So this is linked to how the data is represented, in classical network and how it is different in the quantum network. Slow data processing, and there are many different challenges that today's classical internet has. On the quantum internet, it has some features which I will describe shortly, such as superposition and entanglement, and we can use these properties, quantum properties, to build the quantum network and to secure the transmission of the quantum data. And we can make the network energy efficient. We can have exponential speed up in processing, and which is directly coming through the superposition and entanglement actually. And how these the applications can run in an exponential faster way compared to the how we do the classical computing. Okay, so some application I already mentioned, for example, quantum computing or quantum networking and security. So if the why the quantum computer has become a, let's say, the big buzzword today is mainly also, if the quantum computer comes, then there is a fear that the today's classical public key cryptography algorithms can be break, right? All you need is to find the right correct key, right? And which quantum computer can find it in a reasonable amount of time. Of course, it provides the secure communication through quantum key distribution and other protocols, and it enables the enhanced sensing. Quantum machine learning is another kind of hot topic, people have started working on, and it can be used in solving many complex, algorithms in chemistry and materials. So yeah, but these are still the questions how to do, and because quantum computers are still not available. Okay, so but the quantum market is growing, as you know. Let me drink a bit. Yeah. So as you see, Google has already demonstrated its small, quantum computing, and that started actually the race. Race was already there, but after the Chinese demonstration, couple of years ago, it race has even become even higher. So though there are many different opportunities and industries getting huge funds, especially in the US and the Europe, and of course in China, and India is also slowly catching up, but still there are unreal promises, right, of quantum computing today. If you see that there is no real quantum computers, you can buy 5-6 qubit quantum computer to just to play around, but there won't be any real applications that you can solve. So yeah, there are huge funding. For example, Psi Quantum in the US had billions of dollars of funding to develop the photonic quantum computers. But we will see in the coming decade whether it's true or not, whether they will be able to make a scalable quantum computer. But IBM has also kind of developed 433 qubit quantum processor, so-called Osprey. And if you want to know the real information, like as I have written here, so it will need millions of qubit to break one famous RSA classical encryption in a day or two. So currently we are struggling to get the quantum computer with or processor with few qubits, and we need thousands or millions of qubit. So yeah, that's kind of yeah, there are unreal promises, but unless we work, we will not be able to get the product. And one decade before, people would not have imagined that even 5 or 6 qubit processor will come. So our computer will come. So now let me introduce you about the network evolution itself, because any new technology has its root in the past, right? So to quantum computer cannot, or network cannot be built from scratch, because we already have many from devices to network, so have been already developed, and can we use them? So if you look at the classical networking technology, how they evolved, so basically from vacuum tube to transistor to integrated circuit to personal computer. So it all started in 1940s and slowly developed through the 50s and 60s, and in 80s we had the Macintosh computer. After this devices, development of these devices, right? And then the question was, like, how can we develop some applications, right? And during these 60s, US has the significant, like the very well-known projects funded by the ARPANET, and it had the just few nodes, actually 4 or 5 nodes, and they connected, situated, these nodes were situated over different cities. As you can see, you see University of California, Santa Barbara, UCLA, and two other cities. They connected these nodes and transferred some simple text messages, like, and the new applications such as email came into the existence. And after this network, the simple network and the devices, so many bunch of applications developed in order to facilitate the communication. Transport control protocol or internet protocol was developed in 70s, and Ethernet, and from Ethernet, World Wide Web, today we are connected over the internet. And many, like the Google was another milestone for the as a search engine. Big data in 2010 was kind of started booming because of the powerful computers that we have today, servers, especially the GPUs. After 2010, the question was, what next, right? How can we, what next we can do, right? So that time, the wave of quantum communication, quantum networks, quantum computing, these things came around, right? In 2002, 2007 itself, there was a development of quantum key distribution network in the US. And slowly, the US especially, they started building towards the quantum computers, because once the quantum computer is the main thing, QKD is the kind of, to provide the security, but ultimate goal is to develop the quantum computers. And once we have the quantum computers, the networking role will come. So from 2010, there were lots of development, right? So especially in the quantum processor domain, D-Wave developed many qubit processor, and also memory, and all sorts of the devices were getting developed. In 2019, Google had shown the quantum computing. And if you look at 2025, so Microsoft, they developed Majorana, this topological qubit chip, and also Google has developed its own chip called Willow. So these are the groundbreaking development which will lead to the quantum computer in the coming decade, right? So now the question is, what next, right? You can question again. So quantum internet, people are believing, and that it will be another the groundbreaking invention. And once we have the quantum computers, quantum internet will be kind of, you will see the quantum internet will be realized, right? Okay, so now let me take you back to the little bit towards the physics, quantum physics or quantum mechanics. So in the early 90s, people were not believing in the quantum mechanics postulates, right? So in around 1904, so the Niels Bohr and other scientists, they met in Copenhagen in Denmark, and they formulated the quantum mechanics postulates, which was questioned by Albert Einstein. And even during that time, Richard Feynman said, if you think that you understand quantum mechanics, you don't understand quantum mechanics, and it is still valid today, right? There are postulates which are debatable, which people question today, whether should we agree on that or not. But I mean, it's not all. I mean, I mean, there have been some development. And as you can see, in 2022, 3 physicists have been awarded the Nobel Prize: Alan Aspect, John Clauser, and Zellinger, right? So Zellinger aspect was awarded Nobel Prize for experiments with the entangled photons. Closer was for establishing the violation of Bell inequalities, and Zellinger for pioneering quantum information science. So you might have, if you want to know about the quantum information, then read this book by Nielsen and Chong, and also some lectures are available by Anton Jallinger. So that's one that are very kind of fantastic. So yeah, so there have been development, and as you can see with the progress, and all these things, the development lies on the quantum mechanics principle, which enables the quantum communication, right? And how is it different than the classical communication? That's the key idea. Let's delve into the the basics. How is it different? So I think most of you know already. In classical system, a binary digit, in short we call it bit, is represented as as the name suggests, it's a binary. So means two states. So on state we can say it's a 1, and off state as 0. So basically it's a 2 states, right? 2 states are there. That's why we call it binary, right? When a capacitor is charged, we call it fully on state, and if it is discharged, we call it off state, right? And this is how in memory, I mean, the bit binary digits are stored, right? That's how you can link with the logical bits and the real the quantity that is stored to represent this bit, right? And we call it system must be in a state 1 or state 0, whether a capacitor is charged or discharged, right? So in quantum system, we register a qubit as we call this data or the binary digit as a qubit, quantum binary digit. So we call it in short qubit, right? So if I give you an example, so if you have an atom in the ground state, we can call it a state 0, and then special notation. Not sure if I can write here. Okay. So, okay, it was, okay, we'll see. I have the pen, but, okay, fine. So let me see if I can. Okay, no issue. Yeah. So here, you see the special notation, what you call it, the special like this. This is called a ket notation given by the Dirac. This is basically a vector, right? How you call it a vector. So in quantum, it's defined in that way. And if ground state, you represent the vector 0 or state 0, and excited state you represent as a state 1, right? If I give you the photon example, so photon is, let's say, horizontally polarized or vertically polarized, right? There are two possible, there are many different possibilities of polarization, but let's take these two states and calling them 0 and 1. And this, we can also write this as a H ket is equal to 0, and we basically, this quantum mechanics is nothing but the linear algebra, right? So we can represent it a base called vector called 1 0, and vertically polarized photon we can represent it by 0 1, right? So in this column vector, right, what you see here. So how is it different than the classical? That's the question that must come to you. So because until now what you saw, it's like similar thing, 0 and 1, but quantum mechanics and its postulate allows the system that can be represented in a superposition state, right? So a quantum state psi can be written as a alpha times state 0 plus beta times state 1, right? But with the condition that mod alpha square plus mod beta square 1. This is basically normalization constant. And here, what you see basically plus sign is the superposition state, meaning that this is amazing. We can say that system, we don't know. I mean, if it is a quantum state, we say that it can also be in a superposed state, not in the 0 or 1, but also a combination of 0 and 1, right? So Schrodinger actually, so he came up with the idea with the cat inside a box. We don't know its state, whether it's dead or alive. But he said, oh, it can be at the time. If we don't know, then we can assume it at the same time it's a dead as well as alive. So this was just the proposition. So again, if we want to, let's say, send classical bits, which is stored in a register, let's say 4 bits, and we want to send from a sender called Alice to receiver called Bob, then the Shannon, if you and there is a channel which with the Shannon capacity theorem, we can ensure that these bits are reached from sender to receiver error free, right? If the transmission rate is below the channel capacity, right? On the other hand, if it is a quantum bit, right, in the superposed state, then we will not, we do not, we cannot be ensured that we can transfer it from sender to receiver, right? Why? That there are two basically the problems, and that is has the conflict with the quantum mechanics. In order to transfer from the sender, that's the fundamental of the communication, right? You have to transfer from the sender to receiver to communicate the bit, right? And quantum mechanics says no, you cannot do that. Why? Because of one is called no cloning theorem, right? If I formally state, it says that it is impossible to duplicate an unknown and arbitrary quantum state, right? You cannot copy it. In order to send it, you have to copy this from the register and send it over the wire, right? Or in the free space, right? Which, so you cannot even copy it, right? And to make a duplicate, copy, right? So, and another quantum mechanics, I think most of you have already know this Heisenberg uncertainty principle. It says that it is impossible to know a quantum state because you don't know which state it is in, right? So you cannot arbitrarily, without knowing how is if you have this superposed state, you there will be imprecise measurement, right? So because of these two fundamental, quantum mechanics principles, you will not be able to basically transfer a qubit from source to the destination. How to do that? In the coming slides, we will see that. Okay, so how to transfer the qubit? It's all about the quantum communication, which network it will enable, and all this can be seen. So if I give you the two powerful features of quantum mechanics or quantum computing, then as I said, the superposition, and second one is the entanglement, right? So entanglement, I will describe in the next slide. So before that, let me again reiterate what is a superposition. So let's say this one I wanted to actually write, I'm not sure. So this, okay, here I can write if I do this. Yeah, so let's say, okay, so now I can see. Let's say you want to transmit a string of these bits, right? Right. So these bits, when you generate it, it can be in a quantum superposed state, meaning that it can be probabilistic combination of all these basically bits, right? Bit string, right? So particle can exist in multiple states at the same time, right? This is important until you measure it, of course. So, and this is known as superposition, right? It's not that difficult to imagine. If you, let's say, if you have or let me use another color. If you have an electric field which oscillates along the x-axis, you will call it x polarized. If it is an electric field polarized along the y-axis, it's a I'm not sure if I'm able to draw it in the right way. It can be in the y-axis, but it can also be in the combination of the x and y axis, x and y. So it's basically superposed, and this superposition leads to the uncertainty. We don't know exactly which state it is, right? After we measure it, then of course we will know, but then it will lose the quantum properties. Okay, so let me make the full slide again so that you can see it better. Okay, so as I said, the second let me come back a bit. Second important feature of quantum mechanics is the entanglement. right? So before that, let me define this statistically dependent phenomena. So two classical systems can be statistically dependent. We know from the probability, right? If probability of the joint bit 1 and bit 2 is not equal to probability of bit 1 and bit 2. The quantum entanglement follows from that. If you cannot decompose entangled state, here, okay, yeah, good, it works. Entangled state, uh, entangled state in the product form, then we will call it entangled. Okay, so joint state cannot be factorized, then we will call it entangled. One of the entangled state example is this, the the quantum state, because it is between two particles. So let's say typically it's represented like this, because they are entangled, we say. And let's say particle 1 is in state 0, and at that time particle is 1 is 0 1. So particle 0 is in state 0, and particle 1 in, or let me do it, particle xy, or here it's 1 2. So I should do the same thing, 1 1 2. So particle 1 is in state 0 and particle 2 in state 1, right? Plus or minus, it's a superposition basically. And here this is one state, okay? And another time the particle 1 in state 1, for example, state 1, as I explained to you, whether it's a polarization property you can use, or electron spin, or you can use high electron, the state, excited state or ground state. So on the other hand, at other time it can be in state 1, high state, for particle 1, and at that time particle 2 will be in ground state. Okay, so these two are kind of, if you generate a state this, right? I will in one of the slides we will show how what does this mean, how to generate this. Then we will call it entangled state. John Bill, this is one of the John Bill state, and it's a maximally entangled because it's a highly correlated. Okay, so that maximally correlated state, we cannot factorize it as a sum of state 0 plus 1, it's the simple superposition state or something, so a product of this times something that you cannot do. Okay, let me, okay, so yeah, so the entanglement is a strange correlation, right? So we know the state of the system as a whole, but we don't know the individual pieces unless and until you measure it. And when you measure it, the quantum entanglement is gone, right? So you will get the classical information after measurement, right? So that's the strange correlation. And again, so you don't know whether the cat is dead or alive at the same time. So you can say, I mean, this one of this state is this, and one of the other time it's this, but you don't know which state is coming, right, from the generation, right, from these two, and they are, yeah, correlated. If I give you an example with the atom, so let's say an atom, right, an atom is in cold state, and when it's in cold state, a photon is generated from the left arm, right? On the other hand, when this atom is in excited state or hot state, then the photon is generated in the right arm. So what is the beauty of this entanglement? If I measure here, if I have a photo detector here, and there is a click, photon arriving event, right? I already know what is the state of the atom, right? If it is coming from the left, what will be the state? It will be the atom in the cold state, right? So, and if I get a click here, then I know what is the state of the atom, right? So that time it will be the hot, right? So even though you separate these two entangled particles, thousands of kilometers, then if you measure one, you know the state of the other. So that's the entanglement. And this is what question by Einstein, that how can information propagate at this more than the speed of the light? Because already, the state of the other particles situated at, thousands of kilometers, at the same time. So that was the question, and the John Bell came and he proposed some formulation of the state. If one can generate this kind of a state, then we can prove that they are the classical correlation, it exceeds the classical correlation property, and the particles can be entangled state, and you can have the entangled particles, right? So yeah, so coming to the quantum networks. So quantum networks basically transfers and distributes the quantum information, and in short we call it quantum binded digits or qubits, right? So here in quantum, a single photon can carry physical information, let's say bit 0 or bit 1, right? In classical, what we see that if you want to write bit 1 or bit 0, you represent with let's say on or off state, simple on off modulation, and here each bit, depending on the data rate, will be represented by a pulse of photons, and it can have, you can compute the E equal to h nu formula and how many number of photons, and you can compute the energy in this the bit duration. So typically it will be thousands of photons. So thousands of photons will carry the same one bit or more bit depending on the modulation technique information. On the other hand, in quantum, one bit can carry one or more bits of information, right? So that's the one different property. And this no cloning theorem, right? So this enables the security. Okay, so yeah. So basically, how it enables, as I said to you, that you cannot copy an arbitrary and unknown quantum state. And when I describe this QKD protocol, that time I can tell you how it is used. So basically, yeah, if you cannot copy, basically an eavesdropper or the data that wants to copy it, if there is a presence of that, the receiver will not get to know about this information, and it can find it out. So if there is a presence of eavesdropper. On the another hand, this is very important in quantum networking or quantum internet, is called teleportation. How do you transport? How do you teleport basically a quantum bit from one node to remote node? That will enable basically the quantum internet, right? And it is there are protocols available. There has been demonstration, but distance is still an issue. But yes, it is ongoing work. On the other hand, there is another thing in the classical information can be amplified, right? How do we amplify? Let's say you have a source, and after, if it is a fiber, then its a typical attenuation is 0.2 dB per kilometer. Yeah, per kilometer. So after, let's say, 10 kilometers, you will have the loss of 2 dB, right? And after, let's say, typically 80 kilometers, you need an amplifier, and in order to receive the bits correctly, and that's called the receiver sensitivity. Receive power must be more than the receiver sensitivity. And if I compare this in the quantum transmission, what we saw is the single photon transmission. So there is no signal amplification in the quantum domain. Why? Because if this photon is lost, it's gone. Why we cannot amplify? So you need to understand how the classical information is amplified. So let's say we have a pulse of information, right? It will carry the thousands of photons at the, I'm just showing you as a dash thing, but basically photons with the same phase and same energy will be present, right? And that will, let's say, thousands of photons. If after you can calculate after, let's say, 10 kilometers, how many number of, you can calculate the energy, and you can compute how many photons will be left. Let's say 1000, it will be let's say alpha times 1000, right? So for number of photons will be lost. What classical amplifier will do, it's provides the same additional number of photons in the same phase and with the same energy to add up to the what was the source, or lesser than that, or even more, right? So classical amplifier, but how will you do here? So that's because if it is gone, it's gone. You cannot, even though you provide the new photon, single photon, but it will not carry the same information, right? That's not possible. So this is the one of the main kind of challenges or drawback in the quantum networks. Yeah, so yeah, as I said, I have kind of merged the quantum network topologies with this, because quantum internet as I said, it's basically interconnected networks. So what are different network topologies that will enable the quantum internet, right? So it comes from the classical. What is, I think, see the question, what is chat? Okay, what fault tolerant quantum computing is yet to come? Yeah, so yeah, that's right. Fault computing, quantum computing is yet to come, and as you said, because error correction, quantum error correction is not there yet. So that's the main bottleneck currently, main challenge. What is internet, how it is produced? I think you will get to know soon. What is, as I said, internet is basically interconnected network, right? And which is enabled by set of protocols. We will see the protocol stack. That time I think you will get to know more. But as simple as that, it's not produced, it's like built, right? So you can build a network and you can interconnect with various networks and transfer information. That is the internet, right? Okay. So there are different topologies. So simplest one is the point to point. If you have two nodes, you can interconnect with a single fiber or over the wireless. So you can, yeah. But if you have multiple nodes, you can also connect in a linear chain, right? Like this. So one node is connected to maximum two neighboring nodes, one or two neighboring nodes, right? There is another topology that one can build is the tree topology. So here there is a root node and then the child nodes, right? So basically you can connect different nodes in a different fashion. So tree is one of the examples, and the same thing will be followed, right? So of course each topology has its own the drawback or benefit. For example, if this node wants to communicate with these nodes, how it can go? It needs to go from, I'm not sure, different color. I don't know. Okay, so yeah, so you need to go like this. This is the only way here. There is no fault tolerant in this case, right? There is only one single path, right? So this topology has its own advantage and disadvantage. Another topology is the star topology. There is a central node, and other nodes are basically connected through it. So if this node wants to communicate with this one, then it must go through this central node, right? So this is, if the central node is faulty, then these nodes cannot be, then other nodes cannot be cannot communicate, right? The very kind of one of the easiest and simple apart from the linear one is the ring node. So ring network. So ring network. So it's nodes are interconnected in a ring fashion, right? What you see here. So if any link or node is failed, right? Here, okay, let's say this node wants to connect to node A, node B, want to communicate with this node, right? So it has basically two paths, this way or this way. If there is a failure in link or node on let's say this, still there is a path to go, right? So it's a more fault tolerant than the what you see is a linear or tree or these things. But yes, the today's internet is basically, it's a combination of various various these topologies we will see. And mesh is like any node is connected to anywhere in a different arbitrary manner depending on the need. And yeah, so this several one node can be connected with the several other nodes, but it doesn't guarantee that they are fully connected. So fully connected, each node is connected, directly connected, means directly connected, right? So not hopping over another node, but it's a for example, this node is directly connected. So basically all other nodes is connected to this one, and for this is valid for other nodes as well, right? So these are the typical topology that has been used in internet. And in internet, so various topologies have been utilized depending on where you are located and where what you see. So typically what we see that our devices are in the access network. Access network, if we say that, access part meaning that which access the data, right? So for example, home or whichever which we use our devices. So we have a router, you might have the router in the home, and our cell phones are connected wirelessly to that, and the routers are connected over the wire, or it can be also wireless to the other part of the network. So access part here, we call it in a building or home, we call it personal area network, so LAN network, okay, local area network. And this local area network is connected to the city network, right? We call it metropolitan area network, right? And this metropolitan area network is connected worldwide through the wide area network WAN. This is how internet works, right? So if today I'm here in Netherlands and we are talking to you in India, right? So data is transferred over internet, right? And it passes through various stages of the networks. So, and each of this, what you see here, MAN or LAN or these things have different, they use the different topologies, right? In basically, yeah, you can also call the core networks in the last here. So as I said, how is it different, the quantum internet? So quantum internet task is to transfer the quantum bits of information. On the other hand, classical internet basically transfer the classical bits of information, right? And both of these networks can use the fiber actually. So that's the good thing. Of course, there are some criteria. In quantum, you have to worry about the loss much more than what is in the classical internet. But the same infrastructure can be used. Okay. Of course, we have to see what are the different devices we need to invent, or that is that we cannot use from the classical, right? Yeah, so metropolitan area network. So, okay, this part, what you see here, it's the one term I'm not sure how many of you are from the networking background, but this is passive area network, passive optical network, or it can also be the wireless, access network. And this, the access network is connected to the metropolitan area network, and which is typically in the ring. And this ring network is connected to the wide area network or the core network and so on. And if you see the wide area network, so typically from continents are connected over submarine cables. These are all parts of the networks. What we see, my data, what is going to you now, or maybe I'm not sure, you are not unmuted, so you cannot communicate. But so it's going over the fiber. It can go another way. Another way is the over the satellite, but typically, typically it goes over the fiber. Okay. So if you are connected with for example, now in India also there will be like satellite. You can have a satellite broadband communication, maybe by Geo. Geo is they will actually lease from this Elon Musk company actually. Anyway, because they have the satellites for this providing the broadband network. But anyway, so these are the different way you can communicate over from one part of the world to another part of the world. There is a question I see. If same optical fiber is used, how can we distinguish quantum information from the classical? Yeah, that's a good question. And I'm not sure should I answer now or after some time. So I can give you a short answer. So yeah, so as you see, the single over quantum information can be transferred with the single photons, and the classical, it's a very high what do you say, a high power. And how can we do over the same fiber? No, we typically need the dark fiber. Dark fiber means there is no light, right? Or the quantum signal will be propagated over the dark fiber. And additional, because if you see these cables, there are hundreds of fiber pairs inside these big submarine cables, right? So they are communicated over the dark fiber. But I myself have done the experiments where the quantum signal is co-propagated with the classical fiber on the same fiber. But there are limitation, and there are pros and cons by doing that, and you cannot do it over the submarine cables with thousands of kilometers, right? Obviously, and typically, I mean, people have not demonstrated more than, I mean, there are some demonstration. I will come to that. I think I have the slides. So what is the maximum length they have reached with the quantum data propagation? But yeah, this is how it can be done. So typically we need the dark fiber for quantum data transmission. Okay, so I see there was another question. Can you please suggest what types of topologies are used in different networks, LAN, MAN, WAN? Yeah, so typically LAN, it can be the bus, there is this simple, what you say, the bus. So Ethernet network is used, and over the shared medium, and your computers are directly connected to this. In the metropolitan area network, as you see, it's mostly it's in the city, it's in the ring form. And WAN, it can be mesh, right? So these are the different network topologies are used. So WAN. So there are two the options. You can go over the fiber optical networks, or you can go over the satellite. So yeah, that's how it's being used. Okay. So okay, I see another question. I hope you can see my screen with the question also. I'm not sure. Could you suggest the most promising near-term application of quantum networks? Okay, yeah. So we will see that. So I already spoke to you, like QKD, distributed quantum computing. I mean, most promising. These are all promising. Okay. So yeah, QKD with the quantum key distribution, or in short QKD, it's already product you can buy. That's there. Distributed quantum computing is still far away. Okay, so yeah, QKD actually it's actually from Toshiba and other companies you can buy. So if you are a big rich person, then you can secure your network with the QKD devices too. And what it does, I mean, in this coming slides, I will let you know. Okay, so yeah. Okay, so quantum internet. So what are different components, right? It also applies to the classical internet. Okay, only thing is that some devices we need to change, right? So for example, so we have the computer, personal computer we use, right? Right, personal computer, cell phones, etc. Right. So instead of that, we can have the classical, computer, right? And we connect it in the access through the access point and access network, and then that goes to the router, and the router, and then it is connected over different whether it's I mean, here it's not showing the WAN, but over different networks, right? And different networks goes to the the core network, or the wide area network, and they can be either connected through the cables, the fiber cables, or you can have the wireless, or in the satellite communication also, right? So what is important here is the quantum repeater. Of course, the fibers are there, quantum computer is there, each and individual components what you see here is the quantum router will be there, quantum repeater, and other components, as you see here. So what is quantum repeater, and these things we will get to know in the second half. So what are different quantum internet topologies today? So there are so there are various topologies. I think we will stop in a few minutes. And what you see here is the 200-kilometer Chicago area network, and which my collaborator Professor Prem Kumar here at the University of Chicago he works, and yeah, here. Okay, so, and also, okay, I will answer this question shortly. So wait, also in China, actually, if you see this network on the right side, so there are multiple nodes and they have deployed 4,600. This number I think I had put it last year, so it's even bigger. So around, yeah, say basically thousands of kilometers of network, right? But doesn't mean that it's end to end, but they have built up this network, right? Okay. So, I mean, not in China or Chicago, in Europe also there is a Europe-wide quantum networks, right? Although they may, I mean, up to hundreds of kilometers, they can communicate, but then you need to regenerate the data and to transfer again. How these things are done, we will look at, and that's the one of the goal. In classical communication, having two state makes sense while transmitting data, but having multiple state in quantum communication, how communication happens. Yeah, that is what the quantum advantage is there over classical computing, right? And in fact, communication. So you produce basically the superposed state. That's you can do it. I mean, that's what this Alan Aspect at EPFL Zurich, he demonstrated that theoretically. I mean, since 1900, people have proposed 1950s, 60s, and the bill already gave this state, but no one was able to generate such a state and do experiment. And towards the end of the 1900s, so at TPFL, so Alan Aspect, he transmitted, and then he won the Nobel Prize. So yeah, it's possible. We will see how is it in the superposed state and entangled state, right? Superposed and entangled states can be generated, and how it can be measured, actually, right? So after measurement, it becomes the classical information, right? I'm speaking here, my voice is encoded into digital bits and transmitted over the wireless channel or the wired channel, and then you see it, right? So same thing will be done in the quantum network. So so there will be applications, let's say, and then you digitize the information, 1 0 stream of 1 0, and then you encode this 1 0 information into the quantum signals, right? So quantum states, and then transmit it, right? So that's the thing. Yeah. So should I stop now, or Rajinder ji?
Yes, we can take a break.
Yeah.
We can take a break for 5 minutes.
Okay. Thank you so much. I
Yeah,
will
thank you.
get the water. Thank you.